Alright, so now we're going to apply what we know about electrons, their quantum numbers, their locations, to actually write out the electron configuration for atoms, so to show where the electrons actually are. So first in your notes you have a little table with some of the rules, I guess you could say, for each energy level. So we only show the first 4 energy levels. Most of the atoms that we deal with in this level of chemistry fall into the first 4 energy levels. So we have energy level, I should have written it under it, 1, 2, 3, and 4. Okay. So then I want to talk about the sublevels for each energy level. So energy level 1 can only have S sublevels. Okay. It's a very small energy level. There's only room for an S sublevel. Energy level 2 can have S or P. Energy level 3 can have S, P, or D. Energy level 4 can have S, P, D, or F. So hopefully you can see that as the energy levels increase, the energy levels get bigger, so there's more room for electrons. Okay? So we know that each sublevel can have a certain number of orbitals. So we learned before that S sublevels can have 1 orbital. So the first energy level can only have 1 orbital. We know that P sublevels can have 3 orbitals. So the second energy level can have 4 orbitals because it has 3 P's and 1 S. We know that the D sublevel can have 5 orbitals. So the third energy level can have 5 plus 4 plus 1, 9. And we know that the F sublevel can have 7 orbitals. So we have 7 plus 5 plus 3 plus 1, and we get 16 orbitals for the fourth energy level. Okay, so we know that each orbital can have 2 electrons. So 1 times 2 is 2, 2 times 4 is 8, 9 times 2 is 18, and 16 times 2 is 32. So based on this little chart, we see that the fourth energy level can have at most 32 electrons. The third energy level can have at most 18, the second at most 8, and the first at most 1. Okay, so it doesn't mean it has to have that many, that's just how many it can have. So before we look at the 3 major rules that govern electron configuration, let's look at how we write this kind of stuff out. So I'm going to come back to this piece of paper I had over here. So a way that I would notate an electron's location would be something like 3p4. Okay, so what does this tell me? Let's go ahead and write another one. Let's write 2s1. Okay, so I don't actually write the location of a single electron. What I do rather is I describe the location of sublevels. Okay, so if I write this as a sublevel, the 3 tells me energy level 3. The P tells me it's a P sublevel, so I know it's dumbbell shaped. The 4 superscript tells me it contains 4 electrons. Okay, so I know that the P sublevel can hold up to 6 electrons, so I know it's not quite full. Okay, it only has 4. So this right here, 2 tells me the second energy level. S tells me I have an S sublevel. 1 tells me there is 1 electron in there. Okay, so I know that S sublevels can hold 2 electrons, so I know there's only 1 electron, so it could hold 1 more. Okay, so now let's come back and look at the rules that govern electron configuration. So when I say electron configuration, that just means, you know, where the electrons go in the atom. So the Aufbau principle tells us that electrons go in lowest energy location first. Okay, so electrons must fill the lowest energy orbitals first. Okay, so that seems kind of easy. It seems like you would put 1s first, then you might do 2s, then you might do 2p, then you might do 3s, then you might do 3p, then you might do 3d. And that's true. For the most part, that's right. But it turns out it's not quite that simple, okay? There's a little bit of a trick here that we have to use to determine which of these sublevels is the lowest in energy. So to do that, we use something called the Aufbau Diagram. Okay, so rather than memorizing the order of these sublevels and increasing energy, we can use the Aufbau Diagram as kind of a shortcut to help us figure out which is lowest in energy. 1, 2, 3, 4, 5, 6. Yeah, I'm ready to draw. So I'm going to draw it out. The first time through, you just kind of copy mine down. Wait till I'm done drawing it though, and then we'll kind of make some notes about how to draw this correctly each time. So I start by listing 1s, 2s, 3s, 4s, 5s, 6s, 7s. Okay? So these are the 7 energy levels and their corresponding S sublevel. So now I'm going to go back in the second column and write the P's in. But I know the first energy level doesn't have a P sublevel. So I do 2P, 3P, 4P, 5P. And you could go ahead, oops, sorry, I was trying to talk and write at the same time, 5P. You could go ahead and go all the way to 7P. But to make this chart easier to remember and easier to organize, we stop there. So we take one off the top and the bottom there. So for the next sublevel, I need to go to D. But I see that the second energy level doesn't have a D sublevel. So I go to the third line. I do 3D, 4D, 5D. And again, I could go ahead and go to 6 and 7, but I won't for a reason you'll see in a second. Then I need to write in F. Only the fourth energy level and higher has an F, so I go here and I go 4F. Okay? So it's perfectly okay if you were to write, 7P, 6D, 7D, 5F, 6F, 7F. But I think writing it like this makes it easier to remember. It's a nice little triangle. And these sublevels do exist. There is a 7F. But it only exists in atoms so large that we never deal with them on a regular basis, okay? So now you're probably thinking, okay, you just drew all these out. I'm still going to go in order, right? So that's not actually the case. We draw it in this specific pattern so we can do these arrows I'm about to draw, and we can see the lowest energy sublevels. So I'm going to draw the arrows like this. And rather than striking through, I'm going to kind of put breaks in my arrows so you can see what's going on. And there will be one of these posted typed out as well so you can see it. Okay. So go ahead and take a second break from copying this and watch me read through this. So I'm going to take my pen and I'm going to read these sublevels off in order of increasing energy. So I'm going to start with the lowest energy and end with the highest energy. So I have 1s, 2s, 2p, 3s, 3p, 4s. So as we expect so far. Then I have 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. Then we can continue on, but we left some off at the end. So rather than just going in order 1, 2, 3, 4, 5, 6, 7, I have to follow this pattern. So as electrons enter an atom or enter orbitals, they go in this order. Lowest energy first, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 6s. So now I know that I have to go in this order when I add electrons to an atom. Okay, so this is something that rather than just memorizing it, if you do this enough, you'll probably memorize this. You can just say in your head 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. I've done this long enough, I just have it memorized. So if you get to that point, that's perfectly okay. But if you need to draw this out to solve these problems, that's also perfectly okay. So that's the first rule. These are the orders, or the order that electrons enter sublevels. It's called the Aufbau principle. So the second rule that we're going to look at is called the Pauli exclusion principle. So the Pauli exclusion principle simply says that electrons in an orbital. So how many electrons can be in an orbital? Yeah, that's right. Hopefully you said only 2. No matter what orbital it is, they only hold 2. Must have opposite spins. So we'll say in an orbital must have opposite spins. Okay? So if one electron spins upward, the other electron must spin downward. You can't have 2 ups, you can't have 2 downs. You can just have one, you can have 1 up or 1 down, but you can't have 2 that are matched. Okay, so electrons must have opposite spins. And then Hund's rule is the last one, so we'll say that when electrons enter orbitals of equal energy, one electron enters each orbital before a second electron enters any orbital. That's a lot of words. When electrons enter orbitals of equal energy, one electron enters each orbital before a second electron enters any orbital. So that's a little bit strange. So let's just think about the 2p sublevel. So if you have the 2p sublevel, you know that p sublevels have 3 orbitals. Okay? So we draw orbitals with just little lines like this. Okay? So that would be a p sublevel with 3 orbitals. So if I want to put 3 electrons in the 2p sublevel, so if I have 2p3, I would do 1 electron, 2 electrons, 3 electrons. And you can put them down, okay, but it's standard convention to put your first electron in upwards. Okay, so I put 1 in each of them before I put my second one in any of them. Okay, so if I have, let's just say 3d. So d has 5 orbitals. Okay, so let's just say it is 3d4. So there's 4 electrons in it. I go 1, 2, 3, 4. Okay, so that is how we do it. We don't go in and do this. Okay, we would never have one orbital that is full while we still have one orbital that's completely empty. Okay, so those are our 3 basic rules for writing electron configurations, or determining where electrons fall within an atom. First rule, electrons go in the lowest energy location first. Second rule, electrons in an orbital must have opposite spin. Third rule, one electron enters every orbital of equal energy before a second electron enters that orbital. Okay? So those are the basic rules. So now we need to go and try and use these rules, okay, to write the electron configurations for some atoms. Okay, so there are 2 basic ways that we show the electrons in an atom. Okay, we have the electron configuration notation and the orbital notation. And we also have the noble gas configuration, which is an abbreviation that we'll go back and look at after we get these figured out. So let's start off with a simple atom. Let's start off with lithium. Okay, so I tell you to write the electron configuration for lithium. So the first step is to figure out how many electrons lithium has. So lithium only has 3 electrons. You go to the periodic table, see it's atomic number 3, it's neutral, so you know it has 3 electrons. So I have to put 3 electrons somewhere. Okay, I'm going to fold my paper so I can see it. You can see it on the camera. So now I'm going to use my Aufbau diagram to fill in the electrons. So I start off with 1s. I know that the s sublevel can hold 2 electrons. So now I've used 2 electrons. Then I go to 2s. I know that the 2s can hold 2 electrons, but lithium only has 3 electrons. So I only need to put 1. Okay? So now I'm done. That is the electron configuration for lithium. It has 2 electrons in the 1s sublevel and 1 electron in the 2s sublevel. So I know it's simple here, but always go back and count up your number of electrons. Make sure you have the correct number. You have 2, 3. Okay, this 2 plus this 1 is 3, and lithium had 3, so I know I'm good. So the orbital notation simply shows where the electrons actually are. So I show the orbitals with a line like that. So this is the 1s orbital, that is the 2s orbital. So I have an up arrow and a down arrow, and I have an up arrow. Okay, so we go ahead and put both electrons in 1s before we put 1 in 2s, because 1s is lower in energy than 2s. So you have several more in your notes. Let's go ahead and skip down to carbon. Okay, so the first step is deciding how many electrons carbon has. We know carbon, when it's neutral, has 6 electrons from its atomic number, and there's no charge, so let's do 6. So we have 1s, 2, 2s, it can hold 2. After 2s I go up to 2p. I know 2p can hold up to 6 electrons, but I don't need to put 6. I only need how many more? I've used 1, 2, 3, 4. I only need to have 6 total, so I just have 2 there. So the electron configuration for carbon is 1s2, 2s2, 2p2. And go back and double check myself. There are 2, 4, 6 electrons, so I'm good. So if I want to show the orbital notation, I know that 1s has 1 orbital. I know that 2s has 1 orbital. I know that 2p has 3 orbitals. So I label these 1s, 2s, 2p. So 1s has 2, 2s has 2. Okay, so now you're going to see where Hund's rule comes back into play. 2p only has 2 electrons, so I put 2 electrons in there. So that is the orbital notation for carbon. Okay. Let's go ahead and look at one more of these. Let's go ahead and look at neon. So if you look at the periodic table, you'll see that neon has 10 electrons. So I go through, I start off with 1s2. I know it's 1s2 because s orbitals can hold 2 electrons. I go to 2s, and it's 2 because s orbitals can hold 2 electrons. I go to 2p. They can hold 6 electrons. Do I need 6 electrons? Yes, in this case I do. Okay, so I have 6, 7, 8, 9, 10, so I'm in good shape. That's my electron configuration notation. I go back and I write the orbital notation. Okay, so I'll go ahead and draw it in. One S, 2s, 2p. Okay. So hopefully fairly simple there. Let's go ahead and look at one that is a little heavier, so a little more difficult. Let's look, and typically we only write the orbital notation for these smaller atoms. Okay, we only do it now so you can see what's going on. We'll typically only write the electron configuration notation. So let's go ahead and look at bromine. Bromine has 35 electrons. Okay, so we have to place 35 electrons. So let's go ahead and start off. 1s2, 2s2, 2p6, 3s2. So let's go ahead and stop and see how many we've used up. We placed 6, 7, 8, 9, 10, 11, 12. So we still got a long way to go. So after 3s comes 3p. 3p6, 4s2. Okay, so now I've used 2, 4, 6, 8, 14. I've used 20. So I need to keep going. I need to do 3d. I know that d can hold 10. So I have 3d10. Then I have 4p. Let's see how many more I need to add. I've added 2, 4, 10, 20, 30. Okay, I only needed to add 35, so I need to add 5 more electrons. So 4p can hold up to 6 electrons, but I only need to put 5 in it. Okay, I only need to use up 35 electrons. So before I think I'm done, let's go back and double check my work and make sure that I used 35 electrons. Okay, if you didn't use the correct number of electrons, you know you're wrong. So when I add that up, I get 35, so I think I'm in pretty good shape there. Okay, so you can go ahead and try some more on your own. They follow the same basic process. Really, all you have to know, or we have to know quite a bit, but what you have to apply here to write the electron configurations is you have to be sure and follow the Aufbau diagram, the Aufbau principle, and go in the correct order. You have to make sure you put the correct number of electrons in the correct sublevels, and you have to make sure you do the correct number of electrons for each element. Let's go back up and do one more thing. let's look at the electron configuration for lithium +1. So this one's a little bit different. What does a +1 charge tell us? Okay, so a +1 charge tells us that there is one more proton than there is electrons. So we know charge equals protons minus electrons. I know that the number of protons can never change. Okay, so I know the charge is 1 equals, the number of protons is 3, so I can say 1 equals 3 minus, we'll just say E electrons. So I know that lithium +1 only has 2 electrons. Does that change anything? Yes. If it only has 2 electrons, this can't be its electron configuration. So for atoms with a charge, we have to go back and write a new configuration. So lithium +1 would just have a charge, or excuse me, a configuration of 1s2, okay, because we only have 2 electrons. So the only difference in writing electron configurations for atoms with a charge is you first have to determine the correct number of electrons they have. So rather than just saying lithium has 3 electrons, you determine it has 2 electrons. Once you determine the correct number of electrons, nothing changes there. Okay. So we'll go ahead and get some practice at writing the electron configurations. Then I'll go back and show you kind of a shortcut we use called the noble gas configuration.